Hi, I'm Russell Lindsay, Senior Product Manager with Anritsu. I'm here to demonstrate the real-time analysis capabilities of our new Field Master Pro MS2090A Field Portable Spectrum Analyzer. I have on the table here two spectrum analyzers, both tuned to the 2.4 GHz Wi-Fi Bluetooth bands. Here on the right, we have a typical spectrum analyzer. You see, as it's sweeping through the band, there's quite a bit of activity there. If you were doing monitoring of this, you would see that there are signals in the band. There are signals that cover almost the full 80 or 100 megahertz of the setting here. But it's really hard to see over time what's happening. The signals are bouncing up and down. Some are intermittent, some are fairly stable. If I switch this over to a max hold trace, so if I turn this trace on and reset it, you'll see that it does start to build up a bit of a story. I can see different carriers, I can see how it's happening, I can see some of the power levels, but that's going to quickly fill up over time, and all of the nuance of that data is going to be lost. So with a regular swept spectrum analyzer, the gaps in the processing leave me with questions about what's happening over time. So now, if we switch over to our real-time spectrum analyzer, you can see that the full 110 megahertz bandwidth of the MS2090A shows us everything that's happening within this band over time. The data is summarized into this density display where you see in real time the advertising channels of your Bluetooth signals, as well as the data from the other 37 channels bouncing up and down. You also see several fixed Wi-Fi bands and Wi-Fi channels floating through the back. The data is clearly summarized in the display, and if I switch to a spectrogram view, I can see even more of the information where each of the different Bluetooth carriers, as they move through the channels, are shown clearly here, bouncing in their 2 megahertz channels, as well as the advertising channels as they cycle through their process, and then the fixed Wi-Fi channels and the variable Wi-Fi channels as well. So with the real-time spectrum analysis capability, I'm able to clearly read and see the full story of the band as I go through and analyze the signals. Let's take a look at another example of a possible interferer in a wireless telecom signal. I have here both of my spectrum analyzers are tuned to a similar LTE band. On the regular spectrum analyzer, I can see the signal, I can see its bandwidth, and I can see that it has power, but I don't really know much else that's going on. If I were a technician sent out to the field to troubleshoot problems within this band in a specific area, I wouldn't really be able to tell that there was an interferer there. If I look over at my real-time spectrum analyzer, my density display actually gives me a lot more information about what's happening underneath that signal. I can see here that I have my LTE signal with lots of power, but there's something going on in the middle. I have a CW signal that's jamming part of the LTE signal and interfering with the data that's happening there. So if I'm the technician, I can now identify clearly that there's a signal there, and I can use an interference hunting tool to go find that signal, troubleshoot it, and hopefully solve the problem. The last thing I want to demonstrate is the real-time spectrum analyzer's capability to capture intermittent signals, especially in the field. So what I have set up here is a signal generator that's generating an interferer at 24 gigahertz over the air to my spectrum analyzer. Now the analyzer with 110 megahertz of analysis bandwidth and the 40 megahertz RBW gives us a POI of 2.055 microseconds. A POI represents the minimum duration signal that the analyzer can capture at full amplitude accuracy with 100% probability. So with this 2 microsecond pulse that I'm generating from here, I'm able to see that signal and measure the amplitude. Now this right now is set up to a 20% duty cycle. One of the problems that can happen is if that signal is so intermittent that the duty cycle is long, an analyzer might have a hard time capturing it. You'll see here, if I take this period and I extend it out to where I have a 2% duty cycle, I'm still able to measure the signal. I can even go as far as a 0.2% duty cycle, and I'm still measuring my signal, and I'm still seeing that, and I can measure the amplitude. Now, apart from just the POI, the analyzer is also able to capture much narrower signals. In this case, the minimum detectable signal of the analyzer is 5 nanoseconds. So I'm going to set my signal generator here to generate a pulse that's much narrower than the regular 2 microseconds. In this case, I'm going to go to 20 nanoseconds. I'm going to change my period to 100 nanoseconds. So you can see it a little bit better. You see here I'm still capturing this, and if I drop my RBW down to 10 megahertz, I'm able to actually see the sin x over x characteristics of the pulse that I'm generating. So you can see in the field, if you have interferers that are very intermittent or very narrow, you can still use your real-time spectrum analyzer to capture those signals and identify problems in the field. The MS2090A is the world's highest performance handheld real-time spectrum analyzer. With 110 MHz of analysis bandwidth and 40 MHz of RBW and an almost 2 microsecond POI, you'll be able to take lab-level performance out in the field to solve your most difficult challenges. To learn more, visit us at anritsu.com or contact your local sales representative.